Now, here's the important part for not destroying the driver, and this is what we need to look for every time we see a driver failure on PCM or a transistor, a coil, or a fuel pump driver. We need to watch for the activity of this particular, whoops, drew that the wrong way, diode, okay? What this is going to do is allow power to stay here based on the fact that this blocker will not let power flow back through the ground into the driver. Guys, this reflected energy is exactly what destroys every single PCM injector driver or ignition coil driver that you see go out in a module or a box. 95% of the time it's destroyed by this reflection process. And what's happened is the output device, or in the wiring, depending on where they have it, we've got a failure in that diode. We're going to be taking a look at a current waveform here next to show you exactly how this works and how important this diode is in that pulse width modulated circuit for not wiping out your output devices in your PCM. So that's a quick down and dirty on what is called a tank circuit, okay? Or more importantly, or more accurately, an oscillator that's PCM controlled here, okay, by the logic chip. Now, if we take that basic knowledge of resistors, capacitors, inductors, and transistors to run that fuel pump motor, okay, we've got to be able to flow some current here. Okay, now when we're flowing current is when the danger for flyback voltage exists. Flyback voltage occurs when we are rapidly switching that pulse width modulated voltage to that motor. Okay, now the pulse width modulation in this case is its own electrical commutation. In other words, in an old motor that some of us fossils would remember, you'd take the end cap off, you'd have two brushes and a commutator, which would be a metal slip ring wired to the actual motor windings. In this case, we don't have that. The pulse width modulation is the physical electrical commutation itself, and it's used to drive, in this case, in modern day cars, a DC brushless motor. Now, I promised you I'd stop here and take some questions. Let me just take a quick look at the questions board here and see if we've got anything. Whoops, I just closed it instead of opened it. Okay, we don't. Good, fantastic. Now, I'm going to keep rolling because there's a lot to cover here between now and 1 o'clock. Now, so the basic principle here is to deliver or drive, okay? And when I say drive, I'm talking about this. This here is your driver, okay? This is driving current to the load, okay? So we're going to drive pulsed duty cycled voltage right to the stator windings of the motor at high frequency, which is going to create a magnetic inductance. And guys, if you're taking notes right now, please, I told you to study transistors, study inductance. It is of the utmost importance to understand solenoid and coil operated circuits as well as this motor control, inductance, okay? That's what is being used for AC-like operation of a DC permanent magnet motor. And what it's going to do in the case of three-phase is it's going to pulse that current into the motor at 120-degree intervals to pull magnetically the motor around in a smooth, powerful circle. Now, instead of commutators, brushes, and slip rings, now permanent magnets are used in the rotors of the brushless motors. The outside, or the windings of the motor in this case, are going to be wired to the driver, which is then going to pulse the pulse width modulated power right into the motor windings. So permanent magnets are used in these rotors, and PWM duty cycle is used to control current to the load. Okay, now in the case of PWM, the voltage stays relatively constant. If you ramp it from the lowest current, a fuel pump, let's say, the slowest speed or lowest current to the highest speed or highest current, the difference in voltage, guys, is sometimes less than 1/10 of a volt. I've seen it at 2 or 3/10 of a volt difference, meaning as you increase the current, necessarily the amplitude of the signal will increase, but it will only increase to the engineered limit of current control in that circuit. So when we're looking at pulse width modulation motor controls, we want to remember that voltage is always going to be considered to be stable. Now, because we're using pulse width motor control, okay, our voltage is always going to be averaging around 12 volts or circuit voltage. Okay, our mind might say, oh, well, if we're pulse width modulating it, we're only going to see 6 volts on the circuit. Well, that would be true only if you're using a DVOM that averages the circuit. Okay, then you would most likely see 6 volts on your voltmeter. However, if you're using a scope, your voltage level is going to remain at 12 or 14 or 13.8 volts, whether it's on 10% or whether it's on 90%. Okay, so don't get confused with PWM and the fact that you might think with your DVOM that the circuit's only delivering a real 6 volts to that motor. It is not. Because the signal is the voltage in this case, your scope will show you the real voltage, which is that 12 or 14, where your DVOM, if it's an averaging meter, is likely going to fool you or attempt to fool you by showing you 6 volts, okay? That is a really important distinction when we're diagnosing these kind of systems, okay? Now, the beautiful thing about pulse width modulated control on brushless DC motors is, guess what? Let's just take a fuel pump, for example. In the case of a fuel pump, guys, the engineers have stated very clearly that pulse width modulated brushless DC motors have a 37% higher efficiency rate and a 37 to 39% longer service life than a regular old 12 volt DC fuel pump motor. Why? Well, we're conserving the wear on that motor by pulse width modulating it based on what the engine needs for fuel pressure runtime, okay, on that motor, versus the old school where we'd flip a switch, a relay would come on, and you've got 100% power to that pump the entire time the key cycle's on in that car. If that's a 20-hour ride from, say, Maryland here to Florida, that pump's running for 20 hours. In the case of pulse width modulation, the speed control makes it 37% more efficient and at 37% more longevity on top of that. Big movements in the longevity or how long some of these devices will last. Now, that doesn't mean we don't see build quality problems with these devices. You know, if we talk about fuel pumps failing, you know, AC Delcos and that kind of thing, and I'm not picking on anybody, I'm just saying each manufacturer has their own weaknesses with these motors based on the supplier and the design, right? So the big thing to remember when we're looking at this is from a current control standpoint, to control the speed of that motor is the higher the duty, the higher the current to the load. Voltage will remain necessarily close to the same. Now, the output drivers that we were drawing you here, okay, take several different forms in an automotive platform. You've got a high current transistor known as a MOSFET. The other thing that we see a lot in these vehicles are insulated gate bipolar transistors, which is a very high speed, high current, high voltage switching device. These IGBTs are what are used in the hybrid power assemblies to actually phase the AC power load to the hybrid motors MG1 and MG2 in the case of a hybrid or an EV car, right? So the transistor in the case of, say, a MOSFET driving an ignition coil or an IGBT driving a hybrid motor is basically the device that physically sinks the current from the power through the load to the ground, okay? And that's why reflected energy will burn that sucker right out faster than you can say your name. You know, it cracks me up when you see these guys driving around with a check engine light on and a P0303 misfire for 4 weeks waiting to get the car into the shop. Most of the time, guys, by the time you've waited 4 weeks with that kind of reflection, secondary and ignition reflection traveling back on that primary circuit, it's just frying the transistor and it's working on that PCM every single time that rogue coil fires, right? So it's very important to understand all of the mechanics of how these things work, not just the fact that you've got 12 volts and a ground and a motor in between. We got to be a little bit more savvy than that today to really get that answer on the scope when the circuit goes down and we're looking for the problem. Now, all of these devices, MOSFETs, CFETs, power FETs of all kind, and then your integrated IGBTs are basically known as the drivers, okay? The analog output wire, which is really the only thing we're going to measure unless we crack the top of the box and actually test the transistor, which I've been known to do a few times, and I'm sure you have been too, right? And that's interesting. If you learn how to check power transistors, you can actually go into those PCMs really quickly and check the output drivers pretty nicely, depending on where they're mounted in the box, let's say, okay? But the analog wire from your module to the output device is going to be wired literally directly to this driver inside the PCM, guys. And that's what we need to understand when we're scoping that PCM, at that PCM, is whatever that pin is seeing is what that driver inside the box is seeing right there. Now, if we have the pin coming out of the PCM, that's the piece we can't touch. It's going to be soldered to the pin in the connector harness, obviously, okay? So we can obviously today have many, many problems with pin drag in that realm. And pin drag is something that I love to look at, if possible, before I take the connector apart and actually pin drag it, is I like to just take that wire and just wiggle and manipulate, or pin drag it, if you will, while the scope is hooked up. You'd be amazed at how many sudden circuit glitches you can uncover doing that in this case, looking at these circuits right up at the PCM connector. Now, what's the beauty of that? If I test at the PCM connector and I test the exact same circuits with 2 other channels out at the fuel pump or the load device, guess what I'm doing, guys? If I do the math between the 2 channels, I'm now voltage dropping my wiring at the exact same time that I'm looking at the logic signal and the health thereof, and the output signal and the analog lines going to the load. And if the circuit's live and it's running, I'm looking at the load too. So this is where I say, if we just slowly think about how this thing is constructed and what we're really seeing on the screen, that 15-page DTC chart suddenly becomes a one-screen exercise, right, of pinouts and looking at the circuit and analyzing what you got. Now, flyback is going to occur when we're rapidly switching a coil, a solenoid, or a motor on and off. Flyback is produced when a coil's field is energized or collapsed suddenly. That magnetic energy that is produced, and this is why I want you guys to study inductance. Please go study inductance, write it down, okay? Magnetic inductance or magnetic energy is produced in the circuit. And here's the thing that's important to know. It is that magnetic energy is of the same voltage amplitude and the same current strength as the source that produced it. And what I mean by that is this: if we were to have an open secondary in that coil and that energy has nowhere to go, the inductive energy, not the electrical field energy, okay? The electrical field energy is coming down a wire like this. And that current is flowing in one direction on that wire. But as soon as we get a coil involved, now the circuit changes, because here we have electrical field. And as soon as we get into the coil, the principles of inductance apply. and we start to build a magnetic field around the device. Now that magnetic field, guys, is of the exact same amplitude and current strength as the electrical field, or the PCM, that just produced that voltage and current to drive that motor or coil. Really important diagnostic consideration, which is why I want you to study inductance. It's becoming more and more part of our life.